Welcome to today's session. In this video, we will tackle the problem titled Spiral Matrix 2, a fascinating challenge that involves generating a matrix filled with numbers in a spiral order. This is a great exercise to sharpen your problem-solving skills and explore matrix traversal techniques. Let's dive in. The problem we're solving is called Spiral Matrix 2. The goal is to generate an nxn matrix where the elements are filled with numbers from 1 to n-2 in a spiral order. The spiral starts at the top left corner, and the filling process follows a specific direction. First, we move from left to right across the top row. Then, we go downward along the rightmost column. After that, we move from right to left across the bottom row, and finally, upward along the leftmost column. This cycle repeats for the inner submatrix until all the elements are filled. The input is a single integer n, which must be between 1 and 20, inclusive. The output is a 2D list that represents the spiral matrix. This structure ensures that all numbers from 1 to n-2 are correctly arranged in the spiral order. For example, if the input is n equals 3, the output matrix will be a 3 by 3 grid, filled in spiral order as follows. The top row is filled first with 1, 2, 3. Then, we move down the rightmost column, adding 4. Next, we fill the bottom row from right to left with 5, 6, 7. Finally, the leftmost column is filled from bottom to top with 8. The center of the matrix is completed last with the number 9. This process ensures that the numbers are arranged in a clear spiral pattern, starting from the outermost layer and working inward. Now, let's consider the case where the input is n equals 4. Here, the resulting matrix is a 4 by 4 grid. We start by filling the top row with 1, 2, 3, 4. Then, we move down the rightmost column to add 5, 6, 7. After that, the bottom row is filled from right to left with 8, 9, 10. Next, we move up the leftmost column, adding 11, 12. As we continue spiraling inward, the inner submatrix is filled with 13, 14, 15, 16. Each layer of the spiral is completed one step at a time, ensuring the numbers are arranged in the correct order. For a smaller input, such as n equals 1, the matrix is simply a 1x1 grid containing the single number 1. This is the smallest possible case, where the entire matrix is filled with just one element. The problem also specifies some important constraints. The input n will always be between 1 and 20. The output must contain all numbers from 1 to n-2, and these numbers must follow the spiral pattern described. Special cases to consider include the smallest value of n, which produces a tiny matrix, and the largest value of n, which results in a much larger grid. When n is at its maximum value of 20, the output matrix will contain 400 elements. It's important to ensure that the algorithm can handle this efficiently. Additionally, the spiral pattern must be correct regardless of whether n is odd or even. For instance, matrices with dimensions like 3x3 or 5x5 will have a single center element, while even-sized matrices like 4x4 or 6x6 will have a small central submatrix to fill. Properly handling both edge cases and larger grids ensures the solution works universally for all valid inputs. When approaching this problem, we can consider three main strategies. The first is the brute force approach, which involves directly iterating over the matrix and manually filling in cells in a spiral pattern. Here, nested loops are used to determine the direction, right, down, left, or up, and each cell is filled one by one. However, because we need to track visited cells to avoid overwriting, this method requires additional space, which can be inefficient. Managing these direction changes manually also increases the likelihood of errors. The second approach is the optimized layer-by-layer traversal. Instead of tracking visited cells, we divide the matrix into concentric layers. For each layer, we fill the top row, the right column, the bottom row in reverse, and finally the left column in reverse. After completing one layer, we adjust the boundaries for the next inner layer. This method is efficient, requiring n squared time to fill all cells and 1 space since no extra storage is needed beyond the loop variables. It's simple to implement and works well for square matrices, as it systematically reduces the problem size. Lastly, there's the recursive approach, which fills one layer at a time by reducing the submatrix with each recursive call. A helper function handles layer filling, and the recursion continues until the base case is reached. This method is elegant but comes with its own challenges, such as managing stack space and handling small matrices effectively. The recursive approach, while elegant, introduces some drawbacks. The overhead of maintaining a recursion stack increases space usage, and base cases can become tricky to manage, especially for smaller matrices. Despite these challenges, all three approaches, brute force, optimized layer-by-layer traversal, and recursion, share the same time complexity of O(n²), as each cell is filled exactly once. However, the space complexity differs, making the optimized approach the most practical. For this problem, we've chosen the layer-by-layer traversal as our strategy. This decision is based on several key observations. First, the spiral filling process naturally lends itself to being broken down into concentric layers, moving from the outermost layer to the innermost. Second, using boundaries, namely top, bottom, left, and right, to define these layers simplifies direction changes and removes the need for a separate data structure to track visited cells. Finally, by systematically reducing the boundaries after each layer is filled, we ensure that every cell is filled exactly once without overlap or redundancy. The chosen approach stands out for several reasons. In terms of efficiency, it achieves the optimal time complexity of O(n²), as every cell is filled exactly once, and it does so with O(1) space by only using loop variables and boundary markers. Its simplicity lies in the clear logic of using boundaries, which avoids common pitfalls such as off-by-one errors that can occur when managing direction changes manually. Furthermore, the approach scales well across all valid input sizes, starting from n=1. When comparing trade-offs, the brute force method is easier to conceptualize but less efficient due to its extra space requirements. Recursion, while elegant, is less practical for larger matrices because of the stack overhead it introduces. The optimized layer-by-layer traversal strikes the perfect balance between clarity, efficiency, and correctness, making it the best choice for this problem. In terms of final complexity, the time remains O(n²), as each cell is processed once, and the space is O(1), as no additional data structures are used beyond the boundary variables and loop counters. The goal of this problem is to fill an mxn matrix in a spiral order, starting from the top left corner and progressing clockwise. This means we'll move right across the top, then down the right side, then left across the bottom, and finally up the left side, repeating this process layer by layer until the entire matrix is filled. To achieve this, we begin with a few important initializations. First, we define the dimensions of the matrix, m rows and n columns. Then, we establish 4 boundary variables, top, bottom, left, and right, which will help us keep track of the unfilled regions of the matrix. Initially, top is set to 0, representing the first row, and bottom is set to m1, representing the last row. Similarly, left starts at 0 for the first column, and right is initialized to n1 for the last column. We also initialize a variable called current to 1, which will be incremented as we fill each cell in the matrix. Finally, we prepare an empty mxn matrix filled with zeros to store our results. With these preparations, we can now start filling the matrix layer by layer. We begin filling the matrix by processing one layer at a time. First, we fill the top row from left to right. Using a loop that iterates through column indices from left to right, we assign the value of current to each cell in the top row, incrementing current after each assignment. Once the top row is filled, we increment top by 1, effectively moving the boundary inward to the next unfilled row below. Next, we fill the right column from top to bottom. Here, we iterate through row indices from top to bottom, updating each cell in the right column with the value of current and again incrementing current after each step. After completing this column, we decrement right by 1, shrinking the boundary inward from the right. Similarly, we check if there is still a bottom row to fill by ensuring top equals bottom. If so, we proceed to fill the bottom row from right to left, iterating through column indices from right to left. After filling these cells, we decrement bottom by 1. Lastly, if there is still a left column to fill, determined by checking left equals right, we iterate from bottom to top along the left column, updating each cell and incrementing current. After completing this step, we increment left by 1, shrinking the boundary inward from the left. This process continues as long as there are unfilled cells within the boundaries. Once all layers have been processed, the loop terminates when the boundaries overlap or cross, meaning top, bottom, or left, right. At this point, the matrix is fully filled, and we simply return the completed matrix as the result. Let's take a moment to highlight the data structures and key insights that make this algorithm efficient. The primary data structure we use is the 2D matrix itself, which allows us to update elements in constant time. The boundary variables, top, bottom, left, and right, are crucial for dynamically tracking the shrinking unfilled region of the matrix. By controlling the traversal within these boundaries, we ensure that no cells are overwritten or skipped. Additionally, the boundary checks prevent unnecessary iterations, which is especially important for edge cases like matrices with odd dimensions or single rows or columns. In terms of complexity, the algorithm operates in O(m*n) time, as each cell is visited exactly once. It also uses O(1) additional space since all updates are made directly in the matrix itself. To see this algorithm in action, let's look at a 3x3 matrix as an example. We start with top equals 0, bottom equals 2, left equals 0, right equals 2, and current equals 1. First, we fill the top row from left to right with values 1, 2, 3, and increment top to 1. Next, we fill the right column from top to bottom with values 4, 5, decrementing right to 1. Then, we fill the bottom row from right to left with values 6, 7, decrementing bottom to 1. After that, we fill the left column from bottom to top with the value 8, incrementing left to 1. Finally, for the center cell, we assign the value 9 and exit the loop. The result is the completed spiral matrix 1, 2, 3, 8, 9, 4, 7, 6, 5. For edge cases, the algorithm handles scenarios like single-row or single-column matrices seamlessly, as the boundaries naturally adjust to the unfilled region. An empty matrix, where m equals 0 or n equals 0, will return an empty result. Whether the matrix has odd or even dimensions, this approach ensures that all cells are efficiently filled in spiral order. Here, we define a class called solution and implement the generateMatrix function, which takes an integer n as input. We start by initializing an n by n matrix filled with zeros using a list comprehension. This will serve as the structure where we'll place our numbers in a spiral order. Next, we define variables for the boundaries of the matrix, top, bottom, left, and right. These variables help us keep track of the edges as we traverse the matrix. Initially, top is set to 0, bottom is set to n1, left is 0, and right is n1. We also initialize a variable number to 1, which will be used to populate the matrix with numbers from 1 up to n squared. In the while loop, the condition ensures that we continue filling the matrix as long as number is less than or equal to n squared. The first step of the loop handles the top row, where we iterate from the left boundary to the right boundary. For each column in the range, we assign the current value of number to the matrix and then increment number. After completing the top row, we adjust the top boundary by moving it downward. Next, we handle the right column by iterating from the top boundary to the bottom boundary. Again, for each row in this range, we assign the current number value, increment it, and then adjust the right boundary by moving it inward. Finally, we process the bottom row by iterating in reverse, from the right boundary back to the left boundary, filling in numbers as we go. Once the bottom row is filled, we adjust the bottom boundary by moving it upward. Then, we handle the left column, iterating from the bottom boundary back to the top boundary. For each row in this range, we assign the current value of number to the matrix and increment number. After completing the left column, we adjust the left boundary by moving it inward. The loop continues this process in a spiral pattern, shrinking the boundaries inward after each layer is filled, until all numbers from 1 to n squared have been placed in the matrix. Finally, we return the completed matrix. An example usage of the function is shown where we create an instance of the solution class and call generateMatrix with the input 3. The function will produce a 3 by 3 matrix filled in a spiral order, which is then printed to the console. This implementation efficiently handles the spiral traversal and ensures that all numbers are placed correctly within the defined boundaries. Here, we start by defining a Java class called Solution, which contains the method generateMatrix. This method takes an integer n as input and is designed to return an nxn matrix filled with numbers from 1 to n squared in a spiral order. To begin, we initialize an empty nxn matrix filled with zeros. Next, we define 4 variables, top, bottom, left, and right, which represent the boundaries of the spiral traversal. These boundaries will help us navigate through the matrix layer by layer. We also initialize a variable number to 1, which will be incremented as we fill the matrix. Entering the while loop, we continue filling the matrix as long as number is less than or equal to n squared. First, we fill the top row by iterating from the left boundary to the right boundary, assigning each cell the current value of number and incrementing number with each step. Once the top row is filled, we move the top boundary down by incrementing it. Then, we proceed to the right column, filling it from the top boundary to the bottom boundary while updating number and reducing the right boundary by 1. Now, we focus on filling the remaining 2 sides of the current layer of the spiral. After completing the right column, we move to the bottom row. Here, we iterate from the right boundary to the left boundary in reverse order, assigning the current value of number to each cell and incrementing number accordingly. Once the bottom row is filled, we move the bottom boundary up by decrementing it. Next, we fill the left column, this time iterating from the bottom boundary up to the top boundary. Similar to before, each cell is updated with the current value of number, which increments at each step. Finally, we move the left boundary to the right by incrementing it. At this point, the loop is designed to repeat, continuing to fill the inner layers of the spiral until all numbers from 1 to n squared have been placed into the matrix. After the loop completes, the fully populated matrix is returned. Finally, we include a main method to test the generateMatrix function. Here, we create an instance of the solution class and define the size of the matrix, n, as 3. We then call the generateMatrix method with n as the argument, which returns the spiral-filled matrix. To display the result, we use nested for each loops to iterate through each row and each number within the row. Each number is printed on the same line with a space in between, and after each row, we print a new line to format the output. This ensures that the matrix is displayed in a readable form, showing the numbers arranged in the expected spiral order. This main method serves as a simple demonstration of how the generateMatrix function works in practice. In problem number 59, Spiral Matrix 2, the objective is to generate a square matrix of size nxn and fill it with numbers from 1 to n asterisk n in a spiral pattern. This means we start from the outermost layer and move inward, filling numbers in a consistent clockwise order, right across the top row, down the right column, left across the bottom row, and finally up the left column. For the example where n equals 3, we start by initializing a 3 by 3 matrix filled with zeros. To guide the spiral traversal, we define boundaries, top, bottom, left, and right, which initially cover the entire matrix. We'll also keep a variable number to track the next number to be placed, starting at 1. To begin filling the first layer, we start with the top row. The numbers 1, 2, and 3 are placed from left to right in the first row of the matrix. After this, we update number to 4 and move the top boundary down by 1, narrowing the traversal area. Next, we fill the right column by placing the numbers 4 and 5 from top to bottom. Afterward, number is updated to 6, and the right boundary is moved left by 1. Now we switch to the bottom row, filling it from right to left with the numbers 6 and 7. The bottom boundary is then adjusted upward, reducing the area further. Continuing with the left column, the number 8 is placed moving from bottom to top. After this step, the left boundary is incremented to narrow the traversal area again. At this point, the outer layer is complete. Moving to the inner layer, we now fill the only remaining cell, matrix 1, 1, with the number 9. With number updated to 10, the process concludes since all numbers from 1 to n*n have been placed. The final matrix for n equals 3 is a clockwise spiral, 1, 2, 3 across the top, 4 and 5 down the right, 6 and 7 across the bottom, and finally 8 and 9 completing the center. For the next example, where n equals 4, we follow the same procedure. We start by initializing a 4x4 matrix filled with zeros and defining the boundaries, top, bottom, left, and right, which initially span the entire grid. We set number to 1 to begin filling the matrix. Starting with the top row, the numbers 1, 2, 3, and 4 are placed from left to right. With the top row complete, we increment the top boundary to 1 and update number to 5. Next, we move to the right column and fill it from top to bottom with the numbers 5, 6, and 7. After completing the right column, number is updated to 8, and we reduce the right boundary by moving it leftward. Now we move to the bottom row, filling it from right to left with the numbers 8, 9, 10, and 11. Once this row is complete, the bottom boundary is adjusted upward, and number is updated to 12. Finally, we fill the left column from bottom to top with the numbers 12 and 13. At this point, the outer layer is complete, and we narrow the traversal area again by incrementing the left boundary. With the outer layer complete, we proceed to the inner layer. Starting with the top row of the inner layer, we fill the cells matrix 1, 1, and matrix 1, 2 with the numbers 13 and 14. After this, the top boundary is incremented, and number is updated to 15. Next, we fill the right column of the inner layer, placing the number 15. Finally, we fill the bottom row of the inner layer with the number 16. At this point, all the numbers from 1 to n*n have been placed in the matrix, and the traversal is complete. The final output for n equals 4 is a 4x4 matrix filled in a clockwise spiral order. The outer layer is 1, 2, 3, 4 across the top, 5, 6, 7 down the right, 8, 9, 10, 11 across the bottom, and 12, 13 up the left. The inner layer continues with 13, 14 on the top, 15 down the right, and 16 completing the bottom. The key takeaway is that the solution works by filling the matrix layer by layer in a systematic clockwise direction. The boundaries are adjusted after each layer to narrow the traversal area. The process stops as soon as number exceeds n*n, ensuring all cells are filled appropriately. The time complexity of the generate matrix function is O(n²), and this is due to two main components. First, the initialization step creates an n(x)n matrix filled with zeros. To do this, we iterate through n rows, and within each row, we initialize n elements, leading to a total of O(n²) operations. Next, we have the spiral filling process, where we write numbers from 1 to n² into the matrix. Each of these numbers is written exactly once, and since assigning a value to a cell is a constant time operation, this step also requires O(n²) time. The nested loops within the while loop handle the top row, right column, bottom row, and left column, processing fewer elements as the boundaries shrink. However, when we sum up all iterations across these loops, the total remains proportional to n², confirming the overall time complexity of O(n²). Now, to further justify the time complexity, we observe that the initialization contributes O(n², and the spiral filling also contributes O(n². When combined, the total time complexity remains O(n². Moving on to space complexity, the function also has a complexity of O(n². This is primarily due to the storage of the n(x)n matrix, which requires space for n² elements. Additionally, the algorithm uses only a constant number of auxiliary variables, such as top, bottom, left, right, and number, for keeping track of the spiral traversal. These variables contribute just O(1) to the space usage. Since the matrix storage dominates and no extra recursive calls or data structures are used, the total space complexity is O(n²). When comparing this optimized approach to a brute force method, we can see significant improvements in efficiency. A naive solution might involve making multiple passes over the matrix, repeatedly checking boundaries and visited cells to determine the next position for filling. While this naive approach still results in n² time complexity, it introduces higher constant factors due to redundant computations. The current approach avoids this inefficiency by directly managing boundaries using variables like top, bottom, left, and right, ensuring each element is filled in a single pass. This makes it far more streamlined. In terms of best, average, and worst cases, the time complexity remains n², as every element must be filled regardless of input size. Similarly, the space complexity is consistently n², dominated by the matrix storage. To mathematically validate the big O, the total number of operations is proportional to n², as each of the n² cells is processed exactly once. The space requirement is also driven by the nxn matrix, confirming both time and space complexities as n². When working on spiral matrix problems, there are a few common mistakes to watch out for. One of the biggest pitfalls is not handling edge cases properly. For instance, if the matrix is empty or has only one row or column, it's easy to encounter index errors or even infinite loops during traversal. Another frequent issue involves direction logic errors. This happens when the transition between directions, like from moving right to moving down, is mishandled due to a missed boundary condition. Similarly, failing to correctly update boundaries after completing each spiral layer can cause infinite loops or attempts to access out-of-bound indices. Lastly, incorrect index calculations are another source of trouble. For example, mixing up row and column increments while moving in a particular direction can lead to skipped or overwritten cells, which ultimately breaks the solution. In some variations of this problem, you may be asked to modify an input matrix instead of generating a new one. Accidentally mutating the wrong matrix can lead to incorrect results, so it's critical to pay close attention to the requirements. From an interview perspective, there are key insights to keep in mind. Spiral traversal often relies on recognizing the repetitive pattern of shrinking boundaries, top, bottom, left, and right, and leveraging this pattern can help simplify your approach. Testing edge cases is also essential. Inputs like empty matrices, single rows or columns, and differences between square and rectangular matrices are commonly used in interviews to evaluate your solution's robustness. Additionally, if you're filling a spiral matrix, you can optimize your solution by pre-computing the total number of elements, allowing you to stop as soon as all cells are filled. Lastly, your ability to explain your direction logic and manage transitions between directions is often tested in interviews, so it's important to articulate this clearly to your interviewer. Spiral matrix problems are closely related to several other matrix-based challenges. For example, LeetCode 54 involves traversing a matrix in spiral order, while LeetCode 59, the problem we're discussing here, focuses on generating a spiral matrix of size n by n. LeetCode 73, set matrix zeros, is another matrix problem that requires modifying a matrix based on specific conditions, and LeetCode 118, Pascal's triangle, is a great example of a pattern-based matrix problem. There are also alternative approaches to solving spiral matrix problems. A recursive approach simplifies the logic by focusing on smaller submatrices, but it comes with the trade-off of potential stack overflow for very large matrices. Another method involves simulating movement using a direction array, such as right being represented by 0, 1, and down by 1, 0. This reduces the need for conditionals but can become tricky to debug if direction updates are mishandled. Finally, a layer-by-layer filling approach focuses on filling each side of the matrix, top row, right column, bottom row, and left column, one layer at a time. While this method is intuitive, it requires careful attention to boundary updates to avoid errors. Great job! In summary, we tackled the spiral matrix 2 problem using a brute force approach to generate the matrix in a spiral order. This problem reinforced the importance of systematic traversal and boundary management. Thanks for watching, and don't forget to like and subscribe for more coding solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!